Good evening, High Legh. A pleasure to be back once more to talk to you, this time about Gaia. Gaia, the space telescope which had a 5-year mission to map 1 billion stars. It did that so well, they decided to change its mission to a 10-year mission to map 2 billion stars. Okay, so what I'm talking about this evening is why map the stars in the Milky Way, how can they be mapped accurately, what type of data can we get, and what do we learn from all the data that Gaia has been producing for the last decade plus. So let's start with the obvious. Why bother mapping the stars? So you could say it's a simple enough question, and the most trivial answer to why we map the stars is so that we can look at the sky and then we can find if objects are up there. We can find them again if they're plotted in a star atlas. We can tell if things have moved. We can tell if things have changed, if any new objects appear. But that's a very trivial reason for wanting to map the sky out. As far as Gaia is concerned, a rather better reason is because if we can map out the stars in terms of their position on the sky, not only in the two-dimensional sense, but their position in the three-dimensional sky, their position in the Milky Way, then we can get an understanding of the dynamics of how our galaxy actually works. If we know where the stars are and we know how the stars are moving, then we can understand the history and the future of our Milky Way galaxy. So how do we map the sky? Do we simply take lots of pictures and stitch them together? Well, that works fine for the Earth, but it doesn't work for the sky, mainly because stars move. You don't tend to think of that from night to night, apart from the rotation of the Earth making the sky appear to move. You don't think of the stars actually moving around the Milky Way. But if that's what we're trying to do, then we can't just assume the stars are in fixed positions and take lots of pictures and make a big mosaic. So we have to remember that rule number one is nothing in the galaxy is static. We are moving around the sun is moving, and all the stars in the galaxy are also moving. Not only that, but we have to remember that the problem is not a two-dimensional problem. Knowing only the two-dimensional positions is only part of the story. If we want to know the full three-dimensional dynamics of the galaxy, we have to remember that when we look out into the night sky and we see a pattern of stars, that's almost irrelevant in terms of their actual positions. For instance, Orion there, a familiar constellation, but when we think of where the stars are actually arranged in three-dimensional space, of course, it looks nothing like that. It's just an accident of perspective from where we are on Earth. So if we want to understand the galaxy, we've got to get a two-dimensional and a three-dimensional picture of as many stars as possible to understand our galaxy. And if you think about it, it's not only a question of wanting to understand the Milky Way dynamics, because when you think about stars, remember, if we were to classify stars in the conventional way using a Hertzsprung-Russell diagram, luminosity on the vertical scale, color on the horizontal scale, if we don't know the distance to any of these stars, then we can't actually know the luminosity. We don't know whether it's a bright star a long way away or a dim star relatively close. So without knowing distance precisely, we don't know luminosity precisely. So for instance, if we've got a whitish star, how do we know whether it's a supergiant or a main sequence or a white dwarf? If we're looking at a reddish star, how do we know if it's a supergiant or a red giant or a red dwarf? Again, for the same thing, the same reasons. If we don't actually know the luminosity, then what type of star are we actually looking at? You can get clues from the spectrum, but we really want a precise measure of distance to give us a precise luminosity to know where on the Hertzsprung-Russell diagram any given star is. And it's a bit of an aside, but bear in mind, if we don't actually know the type of star that we're dealing with, then any exoplanets we find around that star, again, we have very limited information. Because if you think of the techniques that are used to find exoplanets, it's always what's the mass of the planet relative to the mass of the star, the host star? What's the size of the planet relative to the size of the host star? If we don't know the type of star we're dealing with, then we've got very little information about any exoplanets that are going around it. So we need distances to understand stars, and we need distances if we want to get a three-dimensional map of the Milky Way. So there's a lot of reasons why we want distances to be accurate. The standard way of doing that is with parallax. I'm sure you're familiar with the idea that if you hold up your finger and blink your two eyes, your finger appears to move against background objects. It's the same sort of idea. The apparent change in position of a star due to the motion of the Earth around the Sun will make a nearby star shift relative to the more distant fixed stars. These diagrams always imply that this is easy because you will simply see a nearby star move relative to fixed distant stars. But there's no such thing as a fixed distant stars. The parallax angle may be small for stars near or stars far, but in practice, all the stars in the galaxy are moving, and therefore there is no such thing as a fixed star. So yes, we can see changes of nearby stars relative to other stars, but relative changes are of no use to us. We want to measure with extreme precision that parallax angle. Remember, these diagrams are extremely compressed because the distance to stars is, of course, light years or hundreds or thousands of light years, and the distance from the Earth to the Sun is only various, 150 million kilometers or so. So this triangle is actually millions of times longer than it is wide at the base. So it's an extremely small angle. If we think about the nearest star, if we had a star, a hypothetical star at 3 light years distance, that parallax angle, because of the motion of the Earth around the Sun, would be 1 arc second. And that defines the distance of 1 parallax second, the distance at which the parallax is equal to 1 arc second. Turns out that that 1 parsec is just over 3 light years, 3.26. And of course, the nearest star is 4 or so light years away. So all stars are more distant than 1 parsec, which means all stars have a parallax angle smaller than 1 arc second. And if the star is hundreds or thousands of light years away, it'll have a parallax angle that is a tiny, tiny, tiny fraction of an arc second. So we're probably used to the idea that an arc second is the sort of, roughly speaking, the smallest thing we can see with a telescope in terms of resolving, for instance, double stars or details on the moon, because that's the resolving power of small telescopes, especially when seen through the turbulent effects of the Earth's atmosphere. But we're talking about a space telescope above the turbulent effects of the atmosphere, and it is trying to get a very, very high precision on these parallax angles in order to give us the distance as accurately as possible. And that is the crux of the problem. Distance is absolutely critical to Gaia's job, both for Milky Way dynamics and for understanding stars and ultimately stellar evolution. For parallax, we absolutely need to know how the star is moving, not simply how this star is moving relative to a slightly more distant star. We need to know the distances as an absolute position on the sky rather than just relative to everything else we can see. And finally, the stars themselves are in motion. So it's not only the fact that as the Earth goes around the Sun, everything appears to move relative to each other, and ultimately we would like relative to an absolute source. But as we're measuring them, the stars themselves are actually orbiting the Milky Way. We don't tend to think of that because it doesn't move very far. Any given star doesn't move very far in only a few years. But with the precision that Gaia has, we should be able to measure those positions, those positional changes of the stars to work out how they are orbiting the Milky Way. So these 3 reasons are the reasons why mapping the Milky Way has taken until now, or until Gaia. 20, 30 years ago, we did not have the technology that would allow us to map billions of stars in the Milky Way to the precision required to give us the motion of the stars as well as the distances to the stars. Okay, we're getting towards the nub of the problem. How can they be mapped accurately? If we want to measure parallax, and remember we're dealing with 2 different factors, this is rather important. There's the apparent motion because of the motion of the Earth around the Sun. That gives us the parallax, that gives us the distance. In addition, there's the actual movement of the star themselves. And somehow we have to untangle those 2 different effects. So that means we need very high precision measurements. Otherwise we can't untangle the apparent motion because of the Earth's motion and the actual motion of the star. So we need high precision And we need this idea of a fixed coordinate system, not simply a coordinate of one star relative to what appear to be some background stars, because we need to know how they are moving as well. So high precision, because the angles are tiny, much smaller than an arc second. And we need a fixed coordinate system because the Earth is in motion and the stars themselves are in motion. So a double whammy that needs a little bit of sorting out. A long time ago, excuse me, back in the 1980s, they said, oh, we can deal with this without needing very high precision. All we need is a bigger baseline. Instead of have a baseline from the Earth to the Sun, 1 astronomical unit, let's send a spacecraft out to 1,000 astronomical units. Then the baseline is 1,000 times bigger, which means it's going to be 1,000 times easier to measure these small parallax angles. So there was this idea, let's take a spacecraft, fly it out to 1,000 AU with an ion drive. Well, it never actually happened. It would have taken 50 years. If they had launched it in the mid-1980s, it would still be on its way. It still wouldn't have got there yet. Bear in mind that 1,000 AU is a huge distance. Even the Voyager spacecraft have only got to 150 AU so far. So it's an interesting idea. Let's make it easier to measure the angles by sending one of our spacecraft a huge distance away and then comparing its measurements with measurements from Earth. Interesting idea, never actually happened. So it's waited until Gaia came along to give us the precision that would allow us to measure distances to stars a great distance away, requiring very high precision. So coming back to this idea of, well, we can't measure the position of one star relative to another, so we need a fixed coordinate system. What's wrong with the coordinate system we have? If you pick up an atlas, it'll give you the positions of stars in terms of right ascension and declination. The analogous, if you like, analogy to longitude and latitude on the Earth. Because remember, right ascension and declination are defined relative to the Earth. The Earth's axis points in a given direction. That is defined as declination 90 degrees. And the celestial equator is simply a projection of the terrestrial equator, the Earth's equator. So why are these two not good enough? They've been used in star atlases since the first Astronomer Royal came along. So why is it not good enough? Well, right ascension and declination are not good enough for mapping out the stars because right ascension and declination are continuously changing. Second by second by second by second, the coordinates are continuously changing. So we look at a map like this and we say, well, it's easy enough to read off the coordinates of a star in right ascension and declination. But if you look at different atlases, for instance, the Norton's Atlas from 1950 and from 2000, these are not the publication dates. These are the epoch dates, the dates at which the star positions are defined on a particular grid. Why do they change? Well, they change continuously, even though the atlases are only published usually to coordinates that defined every 50 years. The coordinates keep changing because the Earth keeps changing. The Earth's axis is precessing. It points to a different chunk of sky. Okay, it takes thousands of years for it to move, but at the precision that we need for Gaia to measure the positions of stars, it effectively changes minute by minute by minute. And if we try to use right ascension and declination, all the objects in the sky would continuously have moving coordinates. We want to fix where they are so that we can tell if they're actually moving or not. So Earth-based coordinates are not good enough. Okay, if we can't use Earth-based coordinates, what about the alternative? What about using the Sun as a reference? The Sun is the center of the solar system? Not quite, no, it isn't. The Sun actually orbits around the center of the solar system because the planets have a finite mass. They're much smaller than the Sun, but the Sun actually moves around the center of mass of the solar system because Jupiter and Saturn and all the other planets are continuously changing their positions. If we map out where the Sun actually is, we find that the Sun actually orbits around the center of mass. This animation is slowing up just to show us that around 2027, the center of the solar system actually lies inside the Sun, whereas a few years ago, the Sun was actually displaced from the center of the solar system, simply because Jupiter and Saturn were on the same side of the solar system, as it were, counterbalancing the Sun. So if we know the Sun goes around the barycenter, what we really ought to have is a coordinate system with that center of mass, the so-called barycenter. That center of mass ought to be the fixed point that we use rather than the sun itself. So the best coordinate system uses the center of mass of the solar system, called the barycenter, uses that as a fixed point. And we know where the Earth is relative to that point, so any measurement we make from the Earth or from any spacecraft at a particular point relative to the Earth, we can work out what the coordinate would be relative to the sun. Sorry, not relative to the sun, relative to the center of the solar system. So that, it was decided, is the best system to use. If we think about what the sky looks like, if we only thought about parallax, then all the stars are continuously moving in ellipses. Some stars are moving quite a lot if they're close. Some stars appear to be moving quite a small amount if they are more distant. So every object in the sky will be going round in small ellipses, depending on which part of the sky we're looking at. And the ellipses are either large or small, depending on distance. And that's one of the things that Gaia wants to measure. In addition, we've got the stars are actually moving around the Milky Way. Now, it takes millions of years to do a full circuit, but on a short enough timescale of a few years, each star will appear to be moving in, roughly speaking, a small straight line. That means, as well as the motion because of the Earth around the sun, when we add in the actual motion of the star, every star is corkscrewing. The entire sky is swimming with every star making a corkscrew. The corkscrew being the result of the two elements that we're trying to untangle. Actual motion through the sky, because the star is moving around the Milky Way center, and the apparent motion, which we want to be able to measure, because remember, the apparent motion, the parallax, that will give us the distance. If it's a big circle, it's close. If it's a tiny circle, it's very far away. And if we can measure the corkscrew, then we can untangle the circular bit due to the Earth's motion to give us distance from the actual motion of the star, which tells us about the dynamics of the Milky Way. So it is no simple problem. Every star has to be tracked such that we can map out the corkscrew of every star, and Gaia was told we want these results for at least 1 billion stars. So it's going to be measuring 1 billion corkscrews to try and work out what's the motion of the star and what's the parallax, and hence what's the distance.
Excuse me.
Yep.
There's a school of thought that suggests that some of the stars we see no longer exist. They're that far away that the light is coming to us long after the star has disappeared.
Very unlikely. We're talking about thousands of years. Yeah.
The time span you're looking at.
Yeah, the stars tend to live for billions of years. Some of them might live a lot shorter than that. Our sun has got a lifetime of 10 billion years. We're talking about stars in the Milky Way, which are thousands of light years away. For galaxies far, far away, if a galaxy is 10 billion light years away, maybe. But for stars in our galaxy, no, these stars basically still exist. So the first attempt to actually untangle this rat's nest of how are we going to figure out what the stars are actually doing, separating distance from actual motion. The first satellite that tried to do this was Hipparchus, given by that particular acronym there. Reverse engineered because they wanted to honor the Greek astronomer Hipparchus, so they tried to engineer an acronym that sounded close, and they did a fairly good job. This was back in the 80s and 90s. The job of Hipparchus was to catalogue nominally something like 100,000 stars with a precision of a milli-arc second, so 0.001 arc second. And the faintest stars it went down to was about Mag 12, not that impressive. In other words, back down to sort of binocular level. If you can't see it in binoculars, it's probably too faint to be seen with Hipparchus as well. The Hipparchus catalogue of 100,000 stars or so, of course, that's only a tiny fraction of the stars in the galaxy. We know the galaxy has got perhaps a few 100 billion stars, so 100,000 is a tiny sample. It's really only our immediate neighbours that Hipparchus was able to measure. So it wasn't really able to tell much about the dynamics of the Milky Way because we're looking only at our immediate neighbours. But at least it could get an idea of what was going on there. And the resolution, 1 milli-arc second. The Hipparchus catalogue was used for quite a while. For instance, it was the first catalogue used by the Hubble Space Telescope to make sure that the Hubble Space Telescope was looking in precisely the direction it thought it was. Okay, moving on from Hipparchus, we come to Gaia. Don't worry about the acronym. The acronym Gaia was the original idea of let's make a space telescope that would give us a fantastic precision for measuring the motion and the parallax of stars. They thought they were going to use a particular technique called interferometry, and so they came up with this title of Gaia, G-A-I-A. They then decided they were not going to use interferometry, but they loved the name. So they kept the name, and so Gaia is the name of the satellite or the space telescope, even though the acronym is no longer relevant. And Gaia was nominally active between the mid-teenies and the mid-20s. So Gaia's mission was to improve on Hipparchus. Hipparchus did a good job, but it only dealt with 100,000 stars. The idea is Gaia is going to deal with 1 billion stars, eventually 2 billion stars, and the precision was going to be nominally 100 times better. Instead of 1 milli-arcsecond, we're now talking about 10 micro-arcseconds. 1 micro-arcsecond being 1,000th of a milli-arcsecond, which is 1,000th of an arcsecond, which is pretty much the smallest angle that we ever have to deal with as amateur astronomers. But here we're talking about 10 millionths of an arcsecond. Higher precision means that we can see even tiny changes in not only the motion of the star at great distance, but also the parallax of a star at great distance, which means we can measure distances much further into the galaxy. In other words, we have a much greater reach. That's how Gaia was able to go to 1 billion stars rather than just our immediate neighbors. It went to much fainter stars, magnitude 20, and they had tiny parallax angles, but with a precision of 10 micro-arcseconds, it's able to determine parallax even at enormous distances. I think we need to take a step back and just remind ourselves how small these angles are, because I'm saying that this is phenomenal precision, and Gaia is all about precision. Without precision, it's nothing. So let's just remind ourselves how small 10 micro-arcseconds is for the precision here. 10 micro-arcseconds, or 100th of a milli-arcsecond. Think of that as the width of a human hair as seen from a distance of 1,000 kilometers. Imagine you were standing in Land's End and you were looking at somebody in John O'Groats holding up a grain of sand. And you can measure the position of the grain of sand to within the precision of the width of a human hair. That's what Gaia is capable of doing. Absolutely phenomenal. But why build a new telescope? Aren't existing telescopes up to the job? Surely the Hubble Space Telescope is fantastic. Can't that do a similar job? Well, we have other telescopes like the Hubble or the Chamonix telescope, previously known as the Large Synoptic Survey Telescope. It's the one sitting in the Vera Rubin Observatory. If we think about the precision and the number of stars that these telescopes could possibly cope with, well, the Hubble certainly is able to do very high precision work. It can certainly measure stellar positions to better than a milli-arcsecond. And it's certainly true that the Chamonix telescope will be able to look at billions of stars. I mean, that's its job. It's now started its job to survey billions of stars and indeed billions of galaxies. But the Chamonix telescope doesn't have the resolution. It only has a resolution nominally of something like 100 milli-arcseconds, nowhere near enough for the sort of thing we want to do. And although Hubble Space Telescope has the precision, it's only actually measured parallax for something like a few thousand stars. If you wanted to say, right, we are going to use one of these telescopes to do the job that otherwise Gaia would do, how long is it going to take? Well, the Chamonix can certainly map out billions of stars in a 10-year program, because that's what it's designed to do. If you ask the Hubble to measure the parallax of stars with its fantastic precision, it can do it in principle, but it would take thousands of years to actually do what Gaia is capable of doing. And that's only if you measure every star once. If you want to measure every star 10 times or 100 times, then the mission would be 10,000 years or 100,000 years. Not really practical. We don't think, despite the fact that Hubble has done really well to last this long, we don't think it's going to last for thousands of years. So how does Gaia actually achieve this phenomenal precision of 10 arcseconds? Gaia is a European Space Agency mission. It was put together with input from lots of different countries. The mirrors, the silicon carbide mirrors, were made in Germany, France, Belgium. The detector was built in the UK, hurrah, and some of the electrical power subsystems were built in British Aerospace in the UK as well. So it's generally across the European, I was about to say European Union, but of course I mean Europe generally, not necessarily EU. The final put together of the final integration was done by a company called Astrium in Toulouse. Astrium is now a subsidiary of Airbus. So effectively, Gaia is an Airbus in space. Think of it that way. It was constructed in the late noughties until about 2012 it was complete. Then it was launched in 2013 and placed in orbit around L2, the Lagrange point L2, in early 2014. Let's just remind ourselves where L2 is. L2 is sitting there 1 million miles above midnight. Remember, noon on Earth is this side facing the sun, midnight is the face away from the sun, and so L2 is a point that is hovering 1 million miles above midnight and sits 1 million miles above midnight. The advantage of being there, the same as the James Webb Space Telescope, the advantage of sitting there is that a sun shield can block all the light from the sun and the Earth and the moon all at the same time and give you an uninterrupted view of deep space without worrying about any of these heat sources, as long as they stay on that side of the sun shield. So the sun shield, just like the James Webb, all important to keep all of this radiation off the sensitive, in this case, mirrors and detectors. We can see the heat shield being tested here in Toulouse. There it is, making sure that it deploys correctly. It also gives you a sense of scale. It's about 10 meters or so across. There's solar panels on the underside to pick up power. And they obviously checked the deployment quite a few times to make sure it did exactly what they hoped it would do, such that once they had sent it off towards L2, it would deploy correctly and then allow it to continue its mission. So again, we come back to the basic question. Okay, it's sitting at L2, but how does it actually achieve this precision? We know that large mirrors produce very precise results. In other words, very precise images. If you want a really tight image of a star, you get a larger scope. Small optics, small lenses, small mirrors produce large star images. If we have a really big mirror, we can produce really tight star images. But surely if we want micro arc seconds, then we can't possibly be talking about a mirror kilometers in diameter. We've just seen Gaia. The heat shield is, the sun shield is 10 meters or so in diameter. So clearly Gaia itself is only a few meters in size. If we actually compare sizes here, the standard graphic of all of the various large mirrors to scale, in the top there, the Gran Telescopio Canarias, the largest telescope in the world at the moment, soon to be overtaken by the extremely large telescope in Chile, in the ESO. The space telescopes are down here in the bottom left-hand corner, and if they don't show up too well, let me just make them a bit bigger so you can see them. There's the James Webb Space Telescope in the bottom left of this rectangle, and you see Gaia has actually got quite tiny mirrors, 1.5 meters by 0.5 meter. They're actually rectangular, and there are 2 of them. So how does Gaia achieve its high precision? Well, it's not through having kilometer-sized mirrors. It achieves it through a combination of instrumental hardware and a novel way of working, a novel manner of operation. So let's have a look at the hardware first. The hardware comprises a detector which is made up of about 100 or so CCDs. It's a gigapixel. Each CCD is about 9 megapixel, and there's more than 100 of them in an array, which I'll describe shortly. That was made by the company E2V here in the UK. And Gaia, although described as a space telescope, it's actually 2 telescopes. It has 2 telescopes pointing in different directions in the sky. And that's, again, crucial to its mode of operation. Both telescopes, this sounds a bit weird, but both telescopes produce images on the same detector. You might think that's a bit crazy. Surely, if you're pointing in two different directions, the last thing you want is to put those two images on top of each other and have a very confused star field in terms of some of the stars are coming from telescope 1, some of the stars are coming from telescope 2. But that is precisely what they do, and it's critical to the way Gaia actually works. The other thing that makes Gaia completely different from most other space telescopes that you've heard of is Gaia spins. And it is not quite spinning at that speed, but it is spinning so that the fields of view of the two telescopes are sweeping out the sky. And so the stars drift across the CCD detector continuously. Gaia does not take images, despite what you might have seen in terms of here's a picture of the sky taken by Gaia. Gaia does not take images. It measures stars. Let's see how it actually does that. Because Gaia is so different from, for instance, what we're used to, the Hubble or the James Webb Space Telescope, you could argue those two telescopes are the same, apart from one works in the visible and one works in the infrared. But the way data is obtained from the chip, the imaging chip, in the case of the Hubble, that's only a chip about 40 by 40 millimeters or so. But the way data is obtained is crucial to the operation. Remember a CCD, a charge-coupled device. A CCD, basically, when light hits it, light is converted to electric charge. And that electric charge is what we want to measure, because the amount of electric charge tells us the amount of light that's arrived. And it's the light that we're interested in. But how do you get from a whole load of charge on a CCD to a whole load of numbers, which is what we're actually interested in? That is critical to what we're talking about. So let me first describe how a CCD works on, for instance, something like the Hubble or the James Webb, or possibly any CCD that you have on your own imaging system. If we imagine a star field, and we think about how the image is built up, generally speaking, the image is obtained in what is sometimes called stare mode, because the telescope stares at a particular patch of sky and doesn't move whilst the exposure is being taken. In the case of the Hubble, it might, for instance, like the Hubble Deep Field, it might stare at a patch of sky, not for simply a few seconds or a few minutes, but possibly a few hours. And for these sorts of telescopes, it's critical that the telescope stays locked onto its target whilst the exposure is taken. So in stare mode, we stare at a patch of sky and slowly the image builds up over seconds or minutes. And as the light hits each of the pixels, only a few of which are shown here, then gradually we build up the image. To read it out, each line of the CCD is shuffled down into a register, and then the register is shuffled across, and each pixel is converted into a number. In other words, the amount of charge in each pixel is measured. Then the next line comes down, and then again, the register is read through pixel by pixel by pixel. It takes about a millisecond to drop each line into place, and it takes about a microsecond to read each pixel and convert its charge into a number that ultimately will tell us how much light arrived at that particular point. And if we do that, and we do it, of course, in a particular way, in a particular direction, once we are done, all of the charge has been removed from the chip, and we now have a whole load of numbers. And of course, if we are careful and we do our bookkeeping correctly, we know precisely where each of these bits of data came from originally, because we have a particular way of reading it out. That's how charge-coupled devices work when you are using it in stare mode. Stare at a patch of sky, expose it, and then read out the data. Right. That is not how Gaia does it. Remember, Gaia is spinning. Gaia is spinning, so the stars are continuously drifting across the CCD. There's no point in taking an image, in the sense that if you try and take an image, you'd just end up with a blur. So what does Gaia actually do? Because the stars are moving, let's say in this case they're moving from top to bottom, the CCD is read out like I've shown before, but it's read out continuously. So in other words, the pixels are continuously shuffling from the top down at exactly the same speed at which the stars are drifting over the CCD array. So the star stays on the same pixel. Once the star reaches the end of the CCD, again, the individual pixels are read out, and then it finds a star, it makes a note of the time. This is the critical bit. It makes a note of the time that the star reached that particular point in the array. It's not worried about taking an image of that star. What it wants to know is how bright is the star and when did it hit that particular point in the CCD array. And that is done for lots of stars over the entire CCD, and indeed the entire array, which I'm about to show you. But this idea of 2 telescopes, 1 detector, isn't that crazy, putting 2 sets of stars on the same set of CCD chips? Not as crazy as it sounds, and there actually is a precedent for this. If you think about it, what does a sextant do? Now, I'm sure that those of you who rely on GPS in your car have got a sextant in the boot, just in case you need to navigate home. But what does a sextant actually do? Well, a sextant is a device in which you look at the horizon, and you also have a couple of mirrors which are used to reflect stars. So you look at the horizon through a little telescope with your eye, and at the same time, a star which might be in a completely different part of the sky, not on the horizon, but it might be, let's say, 40 degrees up in altitude, you arrange your mirrors so that the starlight is seen to be on the horizon. In other words, 2 different sources are on the same detector, the back of your eye. The retina is now picking up 2 bits of information, the horizon and the star. If you do that, then the angle between the horizon and the star is then fixed by those positions of the mirrors. And for navigation, we use the altitude of the star to determine our latitude, and hence where are we in the world. So we're not interested in using it for navigation, but this idea, light from 2 objects, bounces off mirrors so that they appear on the same detector. Human eye in the case of a sextant, a CCD detector in the case of Gaia. But it's the same idea. If we were to do this, then we know precisely the angle between that star and that star because we know these 2 telescopes are pointing in very specific directions. These 2 telescopes are constructed with a very precise angle between them. Doesn't matter what the angle is, as long as we know it very, very accurately. So that as they sweep across the sky on the same detector, we can get the positions of stars over there simultaneously with the positions of stars in a completely different part of the sky. It reduces errors enormously with this particular mode of operation. So that's what a naked Gaia actually looks like. 2 mirrors labeled here primary 1 and 2. Just for the record, that's how big they are, 1.5 meters long, 0.5 meters wide. They don't have to be circular, they don't have to be the same in 2 directions. We want precision in the direction we're scanning or drifting to be much higher precision than the other direction, and hence the mirrors are rectangular. That's just an indication to, again, give you an idea of scale. There's the Astrium technicians putting it together in Toulouse. So let's have a look at a little more detail of this CCD array. A whole batch of CCDs in the array are called astrometrics. They are designed to measure the positions of stars. Remember, effectively, the timing at which star arrives at particular points. Each of those individual CCDs is that size, 5 by 6 centimeters or so, and each pixel, there's about 9 million pixels in each of the CCDs. Each pixel is rectangular. That mirrors the shape, if you'll excuse the pun, of the actual primary mirrors themselves. Much bigger in one direction, so the star images are much tighter in one direction, so we don't want square pixels. In addition to doing all of the timing, we would like to get other information about the star. These are responsible for measuring the timing and the brightness of the star, but there are 2 sets of CCDs before the star hits the astrometrics, and these are called the sky mappers. They are designed and set up in such a way that stars from one telescope will hit one set of CCDs, and stars from the other telescope will hit the second set of CCDs. That's how the computer on board knows which star is which. It's got billions of stars coming across its field of view, but because they are masked in a particular way such that these sky mappers know which telescope they're looking at, they can identify that star came from that telescope, this star came from that telescope, this star came from that telescope, etc. After they've done the astrometrics, they then go through the light goes through a couple of prisms to measure how bright is the star in the blue part of the spectrum, how bright is the star in the red part of the spectrum, a very simple color mapping. And for some of the stars, they will also go through a spectroscope such that they can then determine the complete spectrum of the star. There's also a few other chips in there as well that are responsible for checking the focus and that sort of thing. And in this particular case, the star drift direction is from our right to our left. And just to give you an idea, the actual spin rate of Gaia is much slower than that little animation would indicate. It spins once in 6 hours, which means it takes about 4 seconds for a star to drift across one of the CCDs. So it takes about a minute for a star to drift across the entire array. Given that we've got about 4,000 pixels in each of these CCDs, the star sits on one pixel for about a millisecond before moving on to the next, and then the next, and then the next. We'll see the operation in just a moment. So there's a little animation from ESA that shows us how it actually works in practice. So there we've got the two telescopes. They're color-coded just so we can keep track of which one we're talking about. So they're color-coded cyan and magenta here. So let's have a look at the light that's coming in through the first of the telescopes. It hits the main primary mirror and then bounces around all over the place. Focal length about 35 meters, folded up into Gaia. And then the stars from that telescope hit the CCD array. And we'll come back to that in a moment. Let's just remind ourselves that we've got a second telescope, and that's hitting a different set of mirrors, but ultimately ending up on the same detector. But the sky mappers know which is which. They know whether we're dealing with telescope 1 or telescope 2, which is why they're color-coded here, so you can see which one's which. As a star crosses a CCD, it builds up in intensity, and when it gets to the end, it's read out. So it now knows its intensity and when it arrived at the end. And then it does the same for the next CCD. It reads it at the end there. It knows its brightness. It knows when it arrived. And it does that time and time and time again for the entire astrometrics array. So it takes 10 or so measurements. Then it measures how blue it is, how red it is, and for some of the stars, let's take the entire spectrum of the star. It's not necessarily done for every star because that would be far too much data for Gaia to handle. So at any given time, there are not dozens. This animation implies that there are dozens of stars crossing the detector and lots of them are being read out at the same time. Remember, the sort of cadence we're actually talking about is more like at any given time there might be 500,000 stars on the detector array, and thousands of them will be being read out at any given second. So thousands of stars per second in terms of their brightness and the timing, and that's 24/7 for 10 years. That's basically how much data Gaia has been producing. It's spinning once every 6 hours, and it's precessing around the sun. So the two telescopes are basically one following the other. It takes 6 hours to spin, which means a particular patch of sky is covered by one telescope, and then a couple of hours later, the other telescope, that gives it a very accurate way of determining exactly how fast Gaia is spinning. So it's mapping out a ribbon of sky, which, because it's precessing and it's also going around the sun with L2, that ribbon of sky eventually sweeps across the whole sky. And this particular animation on the bottom right here is color-coded to show how often a particular patch of sky is getting covered by the Gaia telescopes. So you can see it's not uniform. Some bits of sky get covered more than others, but as long as every star gets covered multiple times in one telescope, as well as multiple times in the other telescope, as well as the same thing again a few hours later, as well as the same thing again a few months later, after 10 years, every star has been measured multiple times. And that gives you not only very high precision, it allows you to see how the star has moved month after month after month, which gives us the indication of how the stars are actually moving in the Milky Way. So what data was actually acquired by Gaia? Its original launch was back here in 2014, and it was decommissioned in 2025. Originally, it was a 5-year mission, but then they extended it to a full 10 and a half years. It takes time to analyze the data. Remember, effectively what it's doing is measuring billions of stars multiple times, as well as taking the spectra of a very large number of stars. But ultimately, it's producing billions of timings of when a given star hit a particular detector. And it's doing that dozens of times over a given period, as well as dozens of times over a given year for best part of a dozen years. So it's got huge amounts of data to reduce. So it takes a little while to reduce the data. So data releases come out in batches. There are 7 data releases. You'd think they might number them 1 to 7. No. 1, 2, E, 3, F, 4, 5 are the data releases. The first 2 data releases contained the first year and then the first 2 years of data, which gave you the original data set of values of proper motion and distances of a few million stars. But once they had 2 years of data, they could produce more precise measurements, and that gave them the extension to billions of stars at much greater distances. There was an early data release because people were getting antsy waiting for data release 3. So they gave an early data release which took 3 years of data and gave even higher precision on all of the billions of stars that they'd measured up to that point. When data release 3 came along in 2022, they not only had very precise data on billions of stars, meaning the motions and speeds, velocities, and distances of billions of stars, they also had data on millions of variable stars, lots of galaxies, hundreds of millions of spectra from nearby stars, and by accident, they also picked up something like 100,000 solar system objects, some of which we knew about, some of which we didn't. The reasons that millions of galaxies are rather important is that when you think of it, galaxies are very remote. You pick up the galaxies almost by accident because the most distant galaxies are almost stellar, especially the very bright, very remote ones, quasars, quasi-stellar objects. They look like stars because they are so remote, they virtually show up only as pinpoints. So we can work out the positions of those galaxies very accurately. We can compare, we know their distance by comparing with other telescopes having already measured them. We effectively have got lots of quasars that are so remote, billions of light years away, that their proper motion and their parallax are effectively 0. Remember, parallax is something we can measure for thousands of light years, but if we're talking about billions of light years, the parallax is going to be 1,000,000 times smaller. It's effectively 0. And this is also effectively 0 motion because stars will be moving around the Milky Way, but an object 10 billion light years away is not going to be moving very much. So we can effectively treat all of the galaxies that we see at very high distances, we can effectively treat those as fixed. They are taking the role of the fixed stars that we always thought that we would really want in order to work out whether a star was actually moving or not. So with the center of the solar system as a fixed point and all of these galaxies as fixed points in the sky, we now are able to fix how every star that we are measuring is actually moving. In 2024, there was a focused product release, which is a rather odd name, for let's see if we can do a better job on certain patches of the sky. They decided to take a close look at, for instance, Omega Centauri. They picked Omega Centauri because it is the biggest and densest globular cluster that exists. We know it's going to be a problem if we're trying to measure the positions of stars when there are so many stars, the stars are so close together, it's difficult to separate them. For instance, if we were to zoom into a Hubble Space Telescope picture of the Omega Centauri, we can easily work out what stars, individual stars in terms of their position and their colors. But when we start getting into this region here, even Hubble has difficulty resolving individual stars. So they tried refining the algorithms that they were using to analyze the Gaia data to say, ultimately, we would like to see into the very crowded regions of the center of the galaxy. Let's use Omega Centauri as a touchstone, as a test. Let's see if we can get those algorithms even better so that we can see stars even when they are really close together. And when they tried it on Omega Centauri, after a little bit of refinement, they found more stars than Hubble was able to see. They found 500,000 more stars than Hubble was able to see in the center of these crowded regions. They are now going to apply what they've learned from that, and the next product release, the next data release 4, which is going to be this year. I thought it might be early this year. It turns out it'll probably be later this year. Data release 4 will take everything they've learned about looking at really crowded regions of the sky, and they'll apply it to looking at the center of the galaxy to see how many more stars they can pull out of that data set. It'll be a little while yet, but data release 5 will basically be the entire lot. It'll be all 10 years worth of data, but it's going to take them a few years to get to that point. It'll probably be the end of the decade before they actually have all 10 years of Gaia data analyzed to give us the maximum possible precision of all of the data that gives us all of these distances and all of these positions and motions of all of the stars on an absolute frame of reference. Let's remind ourselves what our Milky Way actually looks like. This is where we are relative to the center. We're about 8,000 parsecs or 25,000 light years from the center. So there's us in the Orion arm. It used to be called the Orion Spur. Somehow it got an upgrade. It's now the Orion arm of the galaxy. Let's take those labels away so we can see it a little more clearly. That yellow dot there is the entire region covered by Hipparchus. Remember, it was 100,000 or so stars, so it very much only looked at a tiny part of our neighborhood in the same spiral arm that we are sitting. Not really representative of the entire galaxy. Data release 2 from Gaia improved on that by pushing that back to the point where in 2018 they could find stars within that green circle. Still not representative of the whole galaxy, but a huge improvement over Hipparchus. The difference between data release 2 and data release 3 was quite remarkable. With the extra precision that they were able to apply, they would get distance at be able to measure distances much deeper into the galaxy, and that green circle was extended from data release 2 to data release 3. So now it's able to go to something like 30,000 light years. The idea, remember that a few light years gives you an arc second of parallax, so any object that is at tens of thousands of light years has got absolutely tiny parallax angles, and yet it's able to determine stars out to that sort of radius. It's having difficulty looking at what's going on in the galactic center itself. Maybe data release 4 will tell us more about what's going on in the bar in the center of our spiral galaxy. So that is not an image. It's often said that this is an image taken by Gaia. It's not. It's only a map. In other words, each pixel here, the brightness has been determined by how many stars did Gaia find in this particular patch of sky. And if it finds a lot of stars, it puts a bright pixel there. If it doesn't find many stars, it puts a dark pixel there. So it's not a photograph, it's only a map of color-coded how many stars in that patch of sky. But of course, it bears a striking resemblance to what we would find if we actually took an image, including the large and small Magellanic Clouds there in the bottom right-hand corner. So, Gaia has produced an awful lot of data. What have we learned so far? Well, remember, one of the reasons that Gaia was put together was to understand the dynamics of the Milky Way. But also, it'll help us understand stars, because not only will it give us the motion of stars, it'll give us the distances to stars, which gives us the luminosity, so that a Hertzsprung-Russell diagram, luminosity on the vertical scale and color on the horizontal scale, that's one of the reasons that Gaia took red and blue measurements as well as luminosity measurements, because that meant it could now generate a Hertzsprung-Russell diagram. Not a cartoon of what we think the Hertzsprung-Russell diagram ought to be, but the actual Hertzsprung-Russell diagram of the huge chunk of the Milky Way. So it's not basically a cartoon. Here it's an actual map of each dot represents one star whose color and luminosity is known. And in the middle there were so many stars, we've replaced the stars with a color coding of yellow being a lot of stars and red being somewhat fewer stars. And out here, there are so few, we can actually label them individually. But now we know that that is the actual Hertzsprung-Russell diagram rather than just a schematic one. Now astrophysicists can look at that and start making deductions about are models of stellar evolution right or wrong, because that appears to be how stars are forming in our Milky Way galaxy. Almost by accident, it was found that there's a lot of other things in there. Once you've worked out the corkscrewing of every star which is moving through the Milky Way and apparently moving because of the Earth's motion around the sun, once you've taken that all out, it was found that some of these stars seem to be doing odd things. They found 20 or so stars, very much like our sun, that seem to be orbiting around something we can't see. So in other words, it's not massive enough to be a black hole, but the only thing that seems to fit the bill is that these things appear to be neutron stars. So there are a whole load of binaries out there where a star like our sun is orbiting a neutron star. This is rather unexpected because we believe neutron stars are born in supernova. If a star went supernova, how come a star like our sun survived right next door to it? So understanding the dynamics of systems like this will help us understand neutron stars as well as these binaries. They aren't that common. We found 20 or so of them, but that's of course after having looked at 1 billion or so stars. So it is very uncommon to find sun-like stars orbiting neutron stars, but there are enough of them to convince ourselves that these things are real. And we've got some explaining to do as to how you can make a neutron star right next door to a star like our sun. We've also come to the conclusion by looking at where the stars are and plotting them all out that our Milky Way is warped. If you look at it from the side, 2 fried eggs back to back, as it were, it's not perfectly symmetrical. It appears to have a warp in it. That was the result of data release 2 telling us that this is where the stars are when we look at the populations. It doesn't appear to be consistent with a perfectly flat Milky Way. Perhaps that's no surprise when we look at other galaxies, this one in particular, 4565. If you look very closely, it's got a dust lane, but the dust lane isn't absolutely down the middle of the actual light from the disk itself. Again, this one appears to be slightly warped. So we had evidence from lots of other galaxies that some galaxies have warped disks, and we suspected that the Milky Way might have a warped disk. Now we know it does, because Gaia has told us, yes, it does, the result of an earlier interaction with another galaxy. When we look at not star positions, but star motions, if we look at how they are moving, if we exaggerate the motion across the sky and, in a sense, play it forward for millions of years, we get an idea of how all the stars around us are moving. Of course, over a period of a few years, they hardly move at all, but we can still work out which direction they're moving and what sort of orbit do they appear to be in around the Milky Way. And that has told us that most of the stars in the Milky Way appear to be orbiting the way you would expect. But some of them aren't. Some of them are orbiting backwards. Some of them are orbiting in weird orbits. Some of them are in very elliptical orbits that seem to dive into the center of the galaxy and then come way out again. What do we deduce by lots of stars being in weird orbits? We deduce that the Milky Way has been disrupted in the past and probably merged with other galaxies, and what we are seeing is some of the stars that are the result of stars in other galaxies merging with the Milky Way and leaving their imprint on the way stars are moving now. So that's effectively what it looks like. It looks like a mess, but astrophysicists can take this sort of data and figure out, once we take out all the stars we understand, what are we left with and what does that tell us about the Milky Way's history? We've always suspected that the Milky Way is the result of mergers of lots of smaller galaxies merging together, interacting with each other, disrupting each other until we end up with the galaxy that we know and love today. We've always suspected that's the case because we see galaxy mergers and galaxy interactions elsewhere in the universe. We've always assumed that the Milky Way is the same. Now we know it is, because now we have the evidence that tells us not only how many galaxies have interacted in the past, we can even pin down some of the timing of when galaxies have interacted with the Milky Way. So this is a very rough timeline over the entire history of the universe, from 0 to 14 billion years, or backwards if you prefer, on the bottom. And there have been lots of encounters with other galaxies. I'm not going to talk through all of them, but for instance, the Enceladus galaxy, where we had an interaction some 4 or 5 years after the 4 or 5 billion years after the Big Bang. The Enceladus galaxy, we think a number of the globular clusters that we currently see in the Milky Way aren't ours. We think those globular clusters actually came from the Enceladus galaxy because of the way they are moving, which is rather different from other globular clusters. And when we look at the metallicity, what is the composition, the chemical composition of the metals that make up these stars, these group appear to be different to this group. And therefore we can determine that they have a different history. And we think that's because we effectively robbed the Enceladus galaxy of some of its globular clusters. And indeed, a number of the stars from Enceladus have now merged with the Milky Way. I'm not going to talk about the other ones, but the other one of interest is the Sagittarius dwarf galaxy on the right-hand side here. That has been interacting with us for quite a long time. Notice that it isn't finished on the right-hand side. It continues. It is still interacting with us. So we think this is what's happened. The Sagittarius dwarf galaxy, this is built out of a model which takes into account all of the star motions that we currently see with Gaia, working backwards to say, how could they have come about by an interaction with the galaxy? We think the Sagittarius dwarf galaxy interacted with us about 6 billion years ago, clipped the edge of the Milky Way, dragged the dwarf galaxy out into a star stream, as it were, and then it clipped us again a second time about 2 billion years ago. And then it's still a big star stream, but then it clipped us again about 1 billion years ago. We can get these timings, not absolutely precisely, but we think this 6 billion, 2 billion, 1 billion is an accurate way of indicating how this particular galaxy has been clipping the Milky Way. It's been disrupted to the point where the galaxy might have been a small, well-defined galaxy in the first place, but now most of the stars in that galaxy have been dragged out into these so-called star streams, or tidal tails if you prefer. One interesting point about this whole interaction is that we know that whenever galaxies interact with each other, we know that results in a new burst of star formation. Again, we see that whenever we look at galaxies that are interacting with each other or crashing into each other, we can see that new star formation is the result of galaxy interactions and galaxy mergers and the tidal disruption of one galaxy with another. So when this galaxy interacted with the Milky Way 5 billion years ago, we know there was a new stage of star formation. And that's when the sun was born. Now, that might be a coincidence, but it might also be that our sun was born 5 billion years ago as a consequence of the Sagittarius dwarf galaxy clipping the Milky Way, producing a whole load of new stars, including us. So it might well be that we owe our existence to the Sagittarius dwarf galaxy happening to come close enough to interact and produce the sun, which are then, of course, all of the planets, and a few billion years later, us. We see these star streams around other galaxies. Again, we assume that if we can see these star streams around other galaxies, maybe we've got them as well. Now we know we have. Some of these star streams are a bit faint. If I invert the image and bump the contrast up, you can see that there's incontrovertible evidence that some galaxies have definitely had interactions with other galaxies which have orbited around them for perhaps billions of years, dragging the stars out into these streamers. This is Messier 63. It looks isolated and it looks very quiet, but if we do the same, we actually find that it has a huge number of star streams out there as well. It has quite definitely had interactions in the past. And again, a little bit of a fuzzy glow, but if we invert it, again, not quite as clear, but we definitely have signs that there are star streams indicating galaxy mergers and galaxy interactions in the past. We see this so often, it's no surprise in a sense that the Milky Way is also the result of lots of galaxy mergers, but it's nice to have the data that shows that rather than just guesswork. Not only can we tell what has happened in the past with, I would argue, amazing precision, the fact that we can tell this many billion years ago this happened and this many billion years ago that happened, but actually, because we're looking at the motion of stars, we can actually say, because of how they are moving now, we can say what is likely to happen in the future. And we can extrapolate to the right-hand side there and say, in the next few million years, well, correction, the next few billion years, we think the interactions with the Sagittarius dwarf galaxy will probably continue. But there's two things that we can quite definitely say are going to happen in the very near future. One of them is that as well as looking at the motion of stars around the Milky Way, the small and large Magellanic Clouds have been in the field of view of Gaia, and even at that enormous distance, it's been able to actually pin down the motion of stars in the Large Magellanic Cloud. And that has told us that the Large Magellanic Cloud will collide with the Milky Way and probably will merge with the Milky Way somewhere between 2 and 3 billion years into the future. And the other interaction that we know is coming, you probably already know this anyway, we are going to collide with Andromeda. Gaia has been able to look at stars in Andromeda, even though they are at a distance of millions of light years. So the parallax is ridiculously small. The data is not that good, but hopefully in data release 4 or data release 5, it might be possible to pin down exactly what the motion of the Andromeda galaxy is. We know it's coming towards us. We're not absolutely sure whether it's a head-on collision or whether the stars in Andromeda are actually moving slightly to one side or the other, such that they are going to clip the Milky Way rather than give a head-on collision. But the fact that we can produce any data of parallax for a star that is millions of light years away is, in my mind, absolutely incredible. So let me finish with a little epilogue. That is where Gaia was, sitting at L2, or technically in a little halo orbit around L2. Data acquisition ended in January of 2025, and it went into a retirement orbit in March of 2025, basically a year or so ago. Retirement orbit sounds so much better than graveyard orbit, which is what some people call it. Basically, if you're orbiting around L2, like James Webb or like Gaia, all you need to do is to give it the slightest nudge away from L2 and it will continue drifting away. You can only sit at L2. It's basically stable as far as a halo orbit is concerned, but James Webb Space Telescope is slowly falling towards the Earth and needs a nudge to push it back to L2 every so often. If you push it beyond L2, it'll just keep going. That's what they did with Gaia. Once you've pushed it beyond L2, it's no longer at a Lagrange point, it's no longer parked. It'll then just go round the sun, as indicated by the red there. So it will continue to go around the sun at a different speed to the Earth, and hence will appear to drift away from L2. As it drifted away, some amateur astronomers actually caught the motion of Gaia, and it will be back every 14 years or so. The final message from Gaia was that one. It was given a set of data to send back to Earth, which was color-coded according to the numbers, and that was the last message we got from Gaia. Is Gaia going to be replaced with another fantastic telescope to measure parallax even further and distances even further? Well, there are people who say what we really need is an infrared version of Gaia, because the center of the galaxy is so dusty. It's crowded, yes, but it's also very dusty. If we had an infrared version of Gaia, we'd be able to see through some of that dust and get even more precise data about what's going on in the center of the galaxy. So there are ideas, but there's no funding. It might happen by 2045, but it's unlikely to be any time before that. So Gaia is not going to be replaced any time in the next 2 or 3 decades, very likely. There will be other telescopes coming online. For instance, next year we've got the Nancy Grace Roman coming online. That's going to be an infrared telescope, which will have a huge field of view compared to Hubble. For instance, if that is the Hubble view of the pillars of creation, then that is the Nancy Grace Roman at the same resolution. It'll see just as much detail as the Hubble, but its chip size is something like 100 times bigger. So when it looks at a particular chunk of sky, it'll get 100 times as much data for every exposure that it takes. So the Nancy Grace Roman will have high precision like the Hubble. It will be able to extend the data from Gaia, but only for a limited number of stars. Much like Hubble would take 1,000 years to scan the sky, the same would be true even with a large chip like this. So the Nancy Grace Roman will probably provide some limited parallax information and distance information, especially in some crowded regions and dusty regions of the galaxy, but it will not in any way replace Gaia or, in that sense, improve on Gaia's data set. The data that Gaia has produced, data release 4, is expected to be about 500 terabytes of data. What's going to happen to all of that data? Well, it's public. Basically, like most of these government agencies, once the data has been produced, it is then released to the public to do what you like with it. A lot of people have sat down and figured out, well, all of this data is telling us this about the galaxy, for instance. So a lot of very clever people have figured out this is how we use the data to tell us something about how the universe works, or how stars work, or how the Milky Way works. A whole load of clever people, probably aided by a few AI tools along the way to help them sift through 500 terabytes of data. You can't sit and look at it all yourself. But along the way, people have taken all this data, all of this motion of stars, the velocity of stars, working out, for instance, galaxy dynamics, the evolution, the mergers with past galaxies, what's going to happen with future galaxies. And remember, although Milky Way dynamics was one of the main reasons for building Gaia, the secondary one was it's also taking hundreds of millions of spectra to tell us about the types of stars and the nature of stars. And from the luminosity and from the color, we can infer the mass and the chemical composition and the age of all of these stars. So with all of this huge amounts of data that are coming out, either in the next data release or the final data release, we're also going to be testing all of our understanding of what we think we understand about stellar evolution, because we're going to have such an enormous data set to test it against. Almost by accident, we've picked up information about neutron stars. It's actually discovered the largest black hole other than the one at the center of the galaxy. It found that by accident. It's also found hundreds of thousands of solar system objects. And by accident, it also found a few exoplanets. Because if you're measuring the positions of stars accurately enough, you'll find some of them wobble because of the existence of a planet going around that star. The next data release, or the one after that, will be of sufficient precision across 2 billion stars that we'll be able to hopefully test our understanding of, are all these stars moving in the way we think they ought to, according to what we think is going on in terms of dark matter and dark energy. So there'll be a test of dark matter and dark energy when the next data releases come out. So Gaia is not just about measuring stars. It has a huge input to all aspects of our understanding of how the universe works. Gaia was once described by 2 words: obscurity and ubiquity. Obscurity because so few people have heard of it. Everybody's heard of the Hubble. Everybody's heard of the James Webb Space Telescope. Not everybody knows of the contribution that Gaia has made. But Gaia data is now in use by every ground-based telescope. It's now in use by every space-based telescope. Gaia data is going to be used by essentially every astrophysical research project for the next 10, 20, 30 years. Gaia data is Gaia's legacy. Thank you all very much.
Thank you.